All right, 2.1 day 3 finishes our introduction to limits, and we're going to talk about right and left hand limits in this video. So up until this point, when you've been finding a limit, we said that you had to approach it from both the left and the right, and the y value had to be the same for each way you went. Today, we're just going to be coming from one way on some of these problems. And the way you're going to know if you're just coming from one direction is going to be this notation right here. So I got the limit as x goes to a, and then I got a plus sign up here where an exponent would be. That plus tells me that we are coming from the right. Okay, so you're walking along the function from the right, so you're walking from right to left towards the given x value. The other way would be from the left. Instead of a positive exponent, it's going to be a negative or a minus sign there in the exponent. So that tells me we're walking from the left. So without further ado, jumping right into the examples, we have three parts to example 1. First one, they want the limit as x goes to 2 from the left. So here's 2. I walk from the left towards my x value of 2, and I see that the y value is going to 1. So that tells me that my limit, as we come from the left, is going to be 0. Okay, so that's right there. We're going from left because of that negative sign right there. For B, they want the limit as we go to negative 2 from the right. So I'm walking from the right, approaching x value negative 2. My y value is going down to 0 as well. All right, C is where it gets fun. You look at it, there is no exponent here. So I'm not coming from left or right. I have to do both. So from the left, we said our limit was going to be 0. From the right, we can't approach it. There's no function from the right. So since our left does not match the right-hand side, we're going to go back to saying that the limit does not exist. Okay, so if there is no exponent here, there's no direction saying which way you need to come from. It needs to match up both ways. All right, example 2, we got a bunch more questions. So here's our function or graph down here. We want various limits here. So the first one is 0 from the right. So I go ahead and look at my function. I approach an x value of 0 from the right. We're going to need a limit of 1. Limit of 0 from the left. I go back down to my graph. I try to walk to 0 from the left. There's nothing over there. There's no line to walk from the left. So that would be a does not exist. 1 from the right. So we go ahead and walk towards the next value 1 from the right. My y value is 1. Walking towards 1 from the left. We come from the left-hand side. We're approaching a y value of 0. We got 3 from the right. So I walk from the right-hand side towards 3. An x value of 3. We're going to get 2. 3 from the left, we walk along our function until I get to an x value of 3. We're approaching a y value of 2. 4 from the left, I'm going to approach a y value of 1. And the limit as x approaches 1. Again, notice there's no exponent there, so it has to match from the left, which is 0, from the right, which is 1. They do not match. So our limit for that scenario is not going to exist. Does not exist. All right, there are also times when we approach an x value that we're not going to have a given y value. And that would be infinite limits, which we look at in example 3. So the graph was provided for you on this one. You may have to do it by hand. That would be something well within the realm of possibility here. But continue what we're doing. 0 from the right. I'm on this function here. I'm approaching 0 from the right. And I look at my function keeps going up, 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 up to infinity. Okay, we got an arrow going up. You're not approaching like a real y. It just keeps going up. From the left, we're coming this way. We go down for forever. So that gives me a limit of negative infinity. And then flat out the limit as x goes to 0. Well, we just found the left and the right. Left and right. They're negative, positive infinity, not the same. So our overall limit as x goes to 0 does not exist. Example 4, we got another rational function for you. The graph is provided again. We're going from 1, we're going to an x value 1 from the right. Value goes up, so that's positive infinity. Going to 1 from the left, function's going down to negative infinity. And then C again wants to know what's the limit. Is it just straight up go to 1? Well, my left, right-hand sides don't match, so that's a does not exist. Going down to the bottom one, I believe this is the last one where the graph is provided. There's no left-right on this. They just want the limit as x goes to 0. So remember, no notation up there from left or right. I do it from both. So from the left, positive infinity. From the right, positive infinity. It matches up. We have a limit of infinity. And then I lied. We got one more graph that's provided for us. So one more rational function. We got negative 3. You look at it as x goes to negative 3. So from the left, it's positive infinity. From the right, it's positive infinity. So that would be our answer. Now, as I mentioned about a minute or so ago, you could be asked to graph these functions, and that's fair game. Remember, before you even graph it, your first step would be to plug your x value in. If I plug an x value in, we got issues, denominator goes to 0. So we go back to our steps where we should probably do some algebra here. So I got x minus 2 up top. That square on the outside just tells me the factor, the quantity squared, shows up twice. And then denominator factors down to x plus 2, x minus 2. At this point, we have common factors, numerator, denominator, that are going to reduce out and leaves us with an x minus 2 up top, x plus 2 down below. All right, for this one, we could go ahead and try to substitute in now. If I substitute in 2 for x, I'm going to end up with a 0 over 4. 0 divided by any number is just going to be 0. So we can actually flat out say that is our limit. If you didn't trust that, you could always go ahead and graph it. Using our skills from Algebra 2, it's a rational function. So I know I'm going to have a vertical asymptote over here at x equals negative 2. And then as we've been talking about, we know we're going to have a hole where a common factor comes into play. Well, if I go ahead plug in 2, we're going to have a hole at 2, 0. So we got that going on right there. I also know we're going to have a horizontal asymptote. Degrees are the same. We're going to talk about this more in the coming days, but degrees are the same. So if I divide my leading coefficients, we're going to have a horizontal at y equals 1. And again, thinking back to Algebra 2, we're going to have a function that looks like this. If you didn't believe me or you're unsure of yourself, you could always make a table to figure out what the branches are going to look like. That's going to be our setup right there for it. For B, we absolutely needed the graph. Well, technically we didn't, but it is helpful. As x goes to negative 2, from the left it's positive infinity, right, negative infinity. They don't match up. Limit does not exist. All right, example 8. Little different, still working with x minus 2's though. If I plug in 2, bad things happen, so we go ahead and go the algebra route. You got x minus 2, x plus 2, x minus 2, common factor, leaves me with 1 over x plus 2. Okay, so that's your setup right there. For the limit as x goes to 2, I would now suggest you just plug in. Flat out plugging in, we are going to have a limit of 1/4. which is also going to double up as our whole because of that reduced factor. Back to rational functions, you're going to have a vertical asymptote at x equals -2. This one is going to have a horizontal at y equals 0 because the degree in the numerator is less than the denominator. Again, we're going to talk about that in a few days. And then we have our whole at 2 1/4. So 1 2 quarter. We're going to have a graph that looks like this. All right, working on the other limits that we have -2 from the right. So as I approach -2 from the right, we're going to positive infinity. If you didn't have a graph here, you could also plug in values that approach -2 from the right. So we could go like with a -1.5, -1.9, so on and so forth. What you're going to find is that your denominator is going to end up being an extremely small number. And when we have a positive number divided by an extremely small positive number, it's going to go to infinity. We could also approach -2 from the left from the graph. We go down to -infinity. Or again, we could plug in values that are just to the left of -2. So like -2.1, negative whatever. And when we plug it in, you're going to get a negative number up top divided by an extremely small number in the denominator. Well, negative divided by extremely small is going to get us to -infinity. For D, the overall limit, you look at it, you got a positive, you got a -infinity. They don't match up, so our limit will not exist for that one either. All right, absolute last example in today's notes and our basics with finding limits. We have an interesting function here. I go ahead, factor out the denominator. I'm getting x plus 2, x minus 2. That tells me that I have vertical asymptotes at a -2, +2. The degree in the numerator is less than the denominator, so we're going to have a horizontal at y equals 0. And then I have 3 regions to fill in. With this, the likelihood of you being asked to graph this by hand, it's very unlikely. But you could plug in test points if you wanted to figure out what is going on in here. It's going to turn out that you got a branch in the bottom left, a parabola in the middle. Let's see if I go ahead and plug in x value of 0. We're going to have a y-intercept around 3/4, it looks like. So let's see if I can do that. Not bad. And then if you plug in a test point over here as well, you're going to have a branch over here. So let's go something like, and mess that up, went over it, but you got a branch down there. The number I'm worried about on this, so even though I messed this up, it's not the end of the world. What we're worried about is x goes to 2. Well, as x goes to 2 from the right, our function is going to be going down to -infinity. So for A, we're going to have a -infinity. And again, we could test this by picking x values that are just bigger than 2. So if I plug in 2.1, you're going to have a negative divided by an extremely small number. So that gets me to -infinity. 2 from the left, so if I were to go with like 1.9, you're going to have an extremely, excuse me, you're going to have a negative divided by an extremely small negative as well. Well, negative divided by a negative, positive, infinity. And then this one didn't ask for the limit, it would just go straight up to 2, but if it did, it would not exist because of the infinities not matching up.